So you were studying the factors affecting the rate of the reaction, and in the previous lectures we have already finished the two factors, and these were the concentration, pressure, and the temperature. So this is our third factor. So how the surface area is going to affect the rate of any chemical reaction. So the first understand what is the surface area. I mean, this is the area covered by the reactant. So let's suppose this is the box, and I'm going to divide this box into the several similar parts. So here the four part are on the upper side, four similar four on the lower side. So it is converted into the 8 parts, and these are also the cube. So in this way, actually, I'm going to increase the surface area of the reactants. So how can you increase the surface area? By reducing the particle size. So this size is actually was big. So you have divided this, or you have cut it down to the several different particles or the smaller particles. So when you reduce the particle size, the surface area is going to increase. So look at this. If this is the only particle, this is having the surface area, and now this is the surface area, and four are there and four are there. There is the surface area covered by the same reactant. So that means now the first conclusion over here is the relationship of the surface area with the size. So if the size is small, then the surface area will be large. So this is our first assumption. So now we are going to look into detail how this surface area is going to affect the rate of chemical reactions. So again, it is very simple that if there is more surface area, that means it is having the more possibility to collide the reactant to each other because of having more surface area. So there is more possibility, and if there is more possibility, that means there is the more increase in the frequency of the collisions. And whereas when there is more frequency of collision, that means there should be more successful collision. So in return, there will be a more uh, rate of the reaction. So again, by increasing the surface area of the reactants, it is going to increase the number of particles over here. Here, this is only the one particle. It is divided into the 8 particles. So with increase the number of particles, that means you are going to increase the exposed area available for these reactant to react together. So in consequence, this is going to increase the frequency of the particles to collide to each other, and in return, there should be a more uh, increased rate of the reaction. So in conclusion, by increasing the surface area, you have exposed more particles. So there will be more collisions. And if there are more collisions, there will be a more rate of the reaction. So the rate of the reaction is directly proportional to the surface area. So this is all about how the surface area is going to affect the rate of the reaction. So we have concluded with first with the surface area with the size, and then with the frequency of the collisions, with the successful collisions, and in return there should be a increasing rate of the reaction. So moving to the fourth factor, this is the nature of the reactant. And the nature of the reactant, ionic substances react faster as compared to the molecular. So what is happening over here? So I have shown over here the two examples. This is again very simple example, one of the acid-base reactions. So when you have the acid or the base, these are the strong acid and this is the strong base. it is completely dissociated into the ions, hydrogen ions and chloride ion. Similar, this is the sodium ion and the hydroxyl ion. So these are present in the ionic form. So when you dissolve all these or you want to react to each other, and you have also observed in laboratory, there is the fast reaction. This hydrogen immediately react with the hydroxyl ion to form the water, and there is the salt formation, sodium and the chloride. So this is the ionic reaction. So actually the purpose here to show if there is the such type of the reaction, they are faster as compared to the other molecules. So this is a molecular reaction. Let's suppose this is the hydrogen gas and oxygen gas are going to react to form the water products. So this is not in the ionic form, this is in the molecular form. So energy is required to break the bond between hydrogen and the oxygen. Then the hydrogen will react with the oxygen to form the water molecule. So that's why these type of the reaction are slow as compared to the ionic reactant. So you can say the rate of reaction in case of the ionic substances is faster. So as compared to the reactant which are present in the into the molecular form. So this is the our four factor, and it is the nature of the reactants. So it is totally you can just compare one of the reactant with the other one, how which one is faster as compared to the other one, or which one is slower as compared to the other one, based on their nature. And the nature we have defined over here is the ionic nature or the molecular nature. Moving to the last one factor, this is the effect of the catalyst on the rate of the reaction, and how this is going to affect the rate of the reaction. So the first have a look over here. Actually, what is the purpose of the catalyst? And you know, the catalyst actually which are going to increase the rate of the reaction. That's why these are the catalyzed. They are catalyst, and you may say that they are going to catalyze the reaction. So now first I'm going to explain you what is the actually the role of the catalyst in terms of the chemical kinetics, because you are learning the chemical kinetics and especially the rate of the reaction. So we will move after on what would be the direct or indirect effect of the rate the catalyst on the rate of the reaction. Just first to understand what is the role of the catalyst. So here, this is one of the example. This is the reaction of hydrogen with the iodine. This H2I2, and this will form the two molecule of the Hi, hydrogen iodide. So this is the activated complex. That means the first there is the energy required to break the bond between hydrogen and the hydrogen and iodine to the iodine. So energy is required, and that's why these having the intermediate bonds. Now if you provide the energy, so these permanent bonds will convert into the weak bond. That's why they are shown over here are the dotted line. So in a similar way, if these bonds are weakened, and similarly there should be the attraction between hydrogen and the iodide, these the bonds are going to be formed. So these bonds are going to be broken down, and these form the bond between hydrogen and iodide. Hydrogen iodide are going to form. So that's why this state is called the intermediate state, and you can call it the activated complex. Now there is the possibility over here. It may convert into the products, or it may revert back to the reactant. And what is the actually the reason over here? It depends on what type of the forces of attraction between the hydrogen and iodide, or hydrogen iodide and the iodide. So if these forces are strong, then of course the product will not form, it will remain in the form of the reactant. And if these forces are strong, that means hydrogen is bonding with the iodide, and similar in this way, then it will convert into the product, and two molecules of the HI are going to form. So this is very briefly written over here. So this is the reactant, and when you provide the energy, that means no intermediate bond are formed. This is the one molecule A, and B, C is another molecule. So there is the intermediate bond between A and B, and also there is the intermediate bond. That means the bond is going to be weakened between B and C with the other molecules, and this is called the transition state, or you can also call it the activated state. And now if this bond becomes permanent, A and B, and it is weakened, then the product is formed, and this is called the AB. You can see this is the new molecule, A and B, and C is another new molecule, and these are called the product. So important over here is to work on the role of the catalyst. So where is the role of the catalyst? So again, understand, I have explained at the start, you would need the energy required to break the bond between the reactant molecules, like it is shown over here. So when you break the bond, the potential energy is going to increase. That means no, they are the more unstable. So that's why the potential energy is increased. So this is the minimum energy, and we call it the activation energy. Activation energy is represented with the value with the symbol E, capital E, small a. It is the activation energy, and it is defined as the minimum energy. This is the minimum energy for this reactants to convert into the product. And in a similar way, if you convert the product to the reactant, and this would be now the minimum energy. So from here, from the product to the activated state, this would be the activation energy required to convert the product to the reactant. So in conclusion, in both cases, if you convert the reactant to the product or product to the reactant, you must need a minimum energy, that is called the activation energy. So actually, I have just explained the way through which the reactants are converted into the product by forming the activated state, and you call it the activated complex, or you can also say it the transition state. These are the same words. So there are the more important point here. One is the activated complex, another one is the activation energy. So again, look at the value. So this is the first. Let's suppose this is the without catalyst, and this is the example. Again, I have plotted the energy, or it is the potential energy with the reaction products mean reactants are converted into the product. So this is the first way, that means without catalyst, and reactants are converted into the product. And from here to here, this is called the activation energy, and it is the same as explained over here. The reactants are converted into the product, and from reactant to the activated complex is the activation energy of the reactant. So in similar over here, from reactant to the activated complex, this is the activated complex, and here it is the without the catalyst. From here to here, this is the activation energy of the reactant to convert into the product without catalyst. So when you add the catalyst, so what is happening actually, this activation energy is going to reduce. So this energy is going to reduce. That means now this is the activation energy. From here to here, this is the activation energy required again for the same reactants to convert into the products. But what is the change over here? It is with catalyst. So actually, this is the role of the catalyst. So what the catalyst has done over here, it has reduced the activation energy, and which we have defined earlier. It is the minimum energy required to convert the reactant to the product. If you do not provide this energy, then the reaction will not going to occur. That means reactants are not converted into the product. So this is must. So catalyst is actually going to reduce this activation energy. Now, actually know what is this effect on the rate of the reaction. When less energy is required, that means no, you can start the reaction with the minimum energy. Let's suppose if this was the 10 kilojoule energy without catalyst, and when you added the catalyst, the energy is reduced. Now let's suppose this is the 5 kilojoule energy. So with no the less energy is required, so the reaction will be faster. So this is the effect of the catalyst on the rate of the reaction. So with catalyst, activation energy is reduced, and with the reduction in activation energy, now your reaction become faster. So look at the same graph. This was the activated complex required more energy. Now this is happening easily. It is coming to this point, forming the activated complex and easily converted into the products. So now it is easier for the reactants to convert into the product in the presence of the catalyst. So there is the direct relationship between the catalyst, the effect of the catalyst on the rate of the reaction. So the reason very briefly is written over here. So what actually the net conclusion over here, what the catalyst has done in this reaction, it has provided the alternative path. The first path was like this. So this is an alternative path. So alternative path by lowering the activation energy. So that means with the lowering in the activation energy, there is more collision of the particles, which required less energy in order to occur. So this is going to increase the rate of the reaction. So this is the effect of the catalyst on the rate of the reaction, and this is the what I have already explained. It's going to lower the activation energy. Particle needs less energy to react. That's why the rate of reaction would be the faster. But here there is another point up to your level to understand over here. This is the same graph, so don't be confused with the what we have discussed before. Again, these are the reactant forming the activated complex converted into the product. This is without catalyst, blue line, and green line with catalyst. So with the catalyst, it has provided an alternative path by reducing the activation energy. Now this is the activation energy in the presence of the catalyst. So this we have already explained. So what is the point to be noted over here is this is the change in enthalpy. Actually, this is going to define the nature of the reaction and whether this is the spontaneous or the non-spontaneous reaction, or in simply you can say if there is the net change in energy, energy is absorbed or energy is released. This is the symbol, and it is called the change in enthalpy. So delta H, we call it the delta H, and this is the change in enthalpy, and it is the energy released or absorbed during the reaction. And here it is released because the reactant from here to here, these are the reactants. So this is the energy of the reactant from here to here, or without catalyst from here. So when it formed the energy, it actually energy of the product is less than as compared to the energy of the reactant. So energy is lost. So that means energy is reduced from this to this point, or you can say energy is released from this to this point. So that's why the change in enthalpy over here is the having the sign of the minus, and you can say this is the energy release for this reaction. But again, the important point over here, in both of the cases, in this case or this case, look at the value of the delta H. The value of the delta H is not going to change. So this is very, very important point. So energy released or energy required for any of the chemical reaction to occur, this value is not going to change. Only what is happening? Only the activation energy is going to change. So this is a misconception. The energy required or absorbed is going to change. This is not going to change, and you can see over here, because this is the difference of energy from the product reactant to the product. So if I, let's suppose if I marking this is the without catalyst, then again it is the energy difference between the reactant to the product. This is the same. And with catalyst, this graph is reduced to this level. The activation energy is reduced. However, again, the difference in the energy between the reactant and the product is the same. So there is no change in enthalpy in the presence or without or with catalyst. So this is the point which I want to actually explain over here. So net, we have concluded there is the direct relationship between the catalyst or the catalyst on the rate of reaction. And the second most important point was there is no change in the net energy, energy absorbed or energy required for any of the chemical reaction. So this is all about our today lecture. And what we have discussed right now, when you increase the temperature, increase the concentration, increase the pressure, there will be the faster will be the rate of the reaction. So this is the net conclusion. And in summary, if as a chemist, if I ask you fast the chemical reaction, or if you want to slow down the chemical reaction, so what would be the controlling factor? And these are all the controlling factor which we have discussed. So here I am going to take only one way of the reaction. That means if you want to make a faster reaction, then what you are going to do, you must choose ionic compounds. And we have discussed, because ionic compounds are faster as compared to the molecular compound. Second, if you take more concentration, then the reaction will be more faster. Third, in case of the gas, if you take more pressure of the gas, if you increase the pressure on the gas, of course the rate of reaction would be the faster. Fourth one we have discussed, if you increase the temperature, it is going to also increase the rate of the reaction, and the reason we have already explained before. And today we have also discussed, if you increase the surface area of the reaction, then the reaction would also be faster. And finally, the effect of the catalyst, if you add the catalyst, increase the concentration of the catalyst, this is also going to increase the rate of the reaction. So this is all over the summary of the chemical kinetics. Actually, we have done the first topic.